Yes, I think we can start, Duncan. Thank you, everybody. We can proceed.
Great. Good morning, all. Hopefully it's warmer where you are than where I am. It's gone down to -3 overnight here. It's very, very cold, but feeling very Christmassy. But still time to squeeze in a couple of webinars, I feel. So today we're going to be doing direct rainfall modeling within TUFLOW. So as an agenda, I'll go over a bit of background. What is direct rainfall modeling? Why we might want to do it. Then have a bit of a discussion about it because direct rainfall modeling is a relatively new kind of thing, and it blurs some of the boundaries between traditional hydrodynamic modeling and traditional hydrology modeling. And there's a lot of misconceptions about direct rainfall modeling, and it's very easy for particularly hydrologists to say no, we don't think it has the kind of processes that we want to represent. Whereas I think more and more we're starting to address those limitations that hydrologists think exist within hydraulic models to make it much more suited for these kind of whole catchment type direct rainfall models. I'll then talk a bit more about direct rainfall modeling within TUFLOW. So in practice, how do we do it? We'll cover spatial rainfall and also the representation of losses. So that's predominantly infiltration losses, but we could do evaporation as well. And then I'll finish off talking about a new bit of functionality called interflow within TUFLOW, which came out in the 2023 release. And gives us very exciting applications, not only with direct rainfall, but also other applications as well. So I'll discuss that and what that's doing. So as I said, we'll start with some background. Modeling rainfall runoff is pretty complicated. There's a lot of processes going on here. And in the past, what we've done is used hydrology models to convert that rainfall to runoff. So there's many approaches that exist. Usually they're pretty regional. In the UK, we have one approach. In different parts of France, there might be different approaches. In Australia, they'll use a completely different approach as well. And those approaches are a combination of analytical approaches and empirical approaches. Certainly the ones in the UK are pretty black box. There's a lot of parameters there, but they have no real physical meaning. There's many unknowns and approximations within that. What hydraulic models are quite good at is propagating that runoff, and propagating that runoff, particularly that runoff that causes inundation. So we use the underlying or the basic physics of fluid flow to do that. With direct rainfall modeling, we use hydraulics to do both the conversion of rainfall to runoff and use the hydraulics to propagate the runoff, causing inundation. So whereas we might have done this as a two-stage process, looking at hydrology first and then the hydraulics, we're using the hydrodynamic models, the hydraulic models, to do both of those components. If we think about how we do catchment modeling or catchment simulation, in the past, we might have, or I guess we'd still do to a certain degree, but we tended to use these kind of lumped approaches, whereby we would take flow at this downstream end from a catchment, and that catchment can compose of various different hydrological features and characteristics and behaviors. So, whether we've got the headwaters, the wetlands, the tributaries, the rivers, or whether we've got storage within reservoirs, that is all lumped into a single set of parameters. So we might have, for instance, a single slope representing that domain. As hardware improved, we could start to split that up and become semi-distributed. So we could split that up into headwaters, the middle of the channel, middle of the catchment, for instance, and maybe look at storage features within there and start to split up our catchment into areas of distinct hydrological behavior. Where we're moving to with direct rainfall is this distributed approach, where we split the whole catchment up into a series of, in TUFLOW sense, a series of grid cells, each of which has their own slope, for instance, has its own material characteristics, can have its own soil characteristics, and therefore, we're spatially distributing the hydrological behavior, and it really allows us to represent the detail of what's going on within the catchment. Then within each cell, within that, we apply rainfall directly to that 2D cell. And then the resulting runoff is a combination of the cell area, the volume or the rainfall depth that we're applying to that cell. We have the losses, whether they be evaporation losses or infiltration losses. And then we represent the roughness characteristics and also the slopes as well. So, certainly the latter two, the roughness and the slopes, are things that we've always been doing from the point of view of hydraulic modeling. But it's this application of the rainfall depth and application of the losses, which is slightly different with direct rainfall. Just a bit of discussion. So a lot of particularly hydrologists come back to us and say, direct rainfall modeling sounds great. It really addresses some of the limitations associated with hydrological models, but there's a lot of downsides to it. So the ones that commonly come out of the UK, particularly, there's a report that's out there. It's been written by various people, and I've spoken to these people at length. They always tell me, direct rainfall modeling is great, but you need a decent DTM. Direct rainfall's great, but the results are quite sensitive to your model cell size or your mesh size. It's got slower run times compared to our lumped or semi-distributed hydrological models. It takes a long time to calibrate these. You're using industry standard parameters outside of their usual parameter range. And then there's a whole host of other things which I'll touch on later. Oh, sorry, just here. Industry acceptance. Is all river flow from direct runoff? Is there some base flow? If so, how do you represent that base flow? Something we've not traditionally represented explicitly with 2D direct rainfall modeling approaches. And then there's also this component of, how do your soils dry during periods of no rainfall, particularly when you're doing a long simulation. So direct rainfall models, work really, really well in those kind of semi-arid and arid environments. But in somewhere, the temperate, humid environments, not all flow reaching a river is overland flow. There is a lot of infiltration and a lot of base flow. And there's a fair amount of research saying, a lot of the water that enters our rivers is old water, water that was in the soil being stored in the soil and essentially being pushed out by new rainfall. So there's a throwaway image here of me potentially going to talk to a hydrologist about direct rainfall. Need to have all these arguments, in advance. When it comes to the first one, decent DTM, LiDAR availability is absolutely key here. I think France, you're in a very similar situation that we are in the UK, where you have pretty much global coverage at quite a high resolution. I think you're even getting some higher resolution data being acquired at this current point in time, with the aim that will be completed by 2026, I think, and that is freely available. And it's the same kind of thing in the UK. We have that data available to us. We have that data readily available and openly available, which is absolutely fantastic. And I think back to when I first started hydraulic modeling, we were using 10-meter shuttle data at times, and you had to pay for that privilege, whereas having this open data is absolutely fantastic. The other one there, so the next one is sensitivity in the mesh size. So I'll give you a bit of a case study. This is a small research catchment in mid Wales. It's so there's two catchments side by side of similar sizes, one of which has a complete grass land cover, and the other has a forested land cover. So they've been very widely measured and observed, because they've got the right next to each other, similar sizes, similar geology, just completely different land covers. What we're focusing on here is the Afon Gui catchment, which is the grassed catchment. So there's within this small catchment, there's 3 control weirs for measuring flow, and there's various rainfall gauges and various other things. We took an event, an observed event, and we applied the rainfall. So we can see the rainfall up here to our model domain, and we ran it for a range of cell sizes. So this is your traditional hydrologist's counter to direct rainfall modeling. They'll say, you know, if you run it with a 40-meter cell size, this is the flow you get out. If you run it with a 10-meter cell size, you know, you're getting a much better correspondence with the observed flows, but the results are dependent on the mesh size. Now, I would argue that if you took a hydrology model and you changed the slope, your results would be different. So exactly the same kind of thing is going to be happening. You are changing the representation of a parameter, and the results differ. Fair enough. But what we have here, you know, clear dependency of the results to the cell size. As you start to reduce the cell size and you start to converge on the topography, your results start to converge on the observed flow. This is the traditional approach within TUFLOW, which uses a single cell elevation, so a single elevation value per cell. If we turn on subgrid sampling, and I don't know if you're overly familiar with subgrid sampling, but what this does is takes into account all the topography in the DTM, regardless of the cell size. If we switch that on, then our results are remarkably consistent across a range of cell sizes. There's a whole host of benefits from a direct rainfall point of view with subgrid sampling, hopefully some of which we'll be able to cover in a later webinar. But from the point of view of this particular webinar, you know, subgrid sampling has such an impact. And you know, if hydrologists are coming to us and saying your results are sensitive to cell size, well, we can switch on subgrid sampling and say, actually, they're not so sensitive to cell size, if at all. So in terms of that sensitivity to mesh size, cell size, the benefit of SGS is really, really important there. So yeah, we've got that little or almost no mesh size dependency. And that allows you to do faster runs. So what we can do, you know, if we ran a 2-meter cell size, our run time is, you know, quite significant. You know, you might as well go out there and pour buckets of water out on the catchment and measure them in a real environment. But what we can do is we can maybe use a 20-meter cell size and get our results back in 1 minute, or a 30-meter cell size and get our results back in 22 seconds. And then we can change those and do the calibration with a coarser cell size, but still be pretty confident that we're going to get the right result. And then when we have to refine the cell size for, you know, mapping purposes or further investigation, you know, our calibration isn't going to change significantly. So, you know, if we use a 20 meters run, you know, that's 525 times faster than a 2-meter run, but similar results. And when you start to do the calibration, you know, that starts to add up. So if you're doing 1,000 runs at the 20-meter cell size, you're going to be able to do that in, you know, 15 hours. Whereas if you use a 2-meter cell size, it's going to take you the best part of a year. So really, really useful bit of functionality that allows you to reduce the cell size, get through those calibration runs pretty quickly, but have pretty consistent results. And like I said, you can always refine the grid size for the final runs, and you should get a pretty similar output. TUFLOW really comes into its own for this kind of thing. So we'll touch on this later when we go into the details, but we specify the infiltration parameters and other parameters, but we within the tsoilf, the TUFLOW soil file. And what we can do is we can use wildcards. So here we have these caret symbols and CL variable or wildcard, and we have the POR variable, and we have the hydraulic conductivity variable here. And what we can do within our TCF is we can say, right, set that variable to a particular scenario that we read into TUFLOW at the batch file stage. So when we run TUFLOW, we read in these various different scenarios. Then what we can do is we can set up a loop within our batch file. We have this TCF here. You'll see that there's a number of tilde S1, tilde S2. These are different scenarios, and we can just feed in different parameters into those and run through a loop. And what this allows us to do is essentially feed those in, run the simulation, and it will just do that, and it will go through all the possible combinations that exist there. And we did this for 2,720 runs. All we're adding is 10 additional lines of text within our batch file. And we did this with a 20-meter cell size, and then we just run, and it ran all those simulations over a weekend. This is the output. So the dotted line there is the observed flow. All the bluey, pinky colors are the various different plots, and then this black line is the one that we reckon has the best fit. We can do Nash-Sutcliffe efficiencies or clean up to efficiencies and get a measure of which one provides us with the best fit. So really, really useful bit of functionality, not only the subgrid sampling, but also the ability to use wildcards and scenarios and that batch file to really plow through these runs very, very quickly. So, in terms of slower run times compared to lumped hydrology models, yeah, it's going to be the case. Those lumped hydrology models have been set up for speed, and there's a whole host of different parameters that they use, different fudges. But with GPU, subgrid sampling, and some of the functionality that exists within TUFLOW really makes that much more easier. So I just go back. Industry standard parameters. So one of the things that came up with this particular study is when we were doing it is that we were looking at the land cover. Most of it is what's termed acidic upland grassland. And if you go to a textbook, the typical value for that is 0.06. TUFLOW also has the capability of doing depth varying roughness, which we'll come on to a bit later on. And we played around with that, but it never really had a great impact. But what we found is that to get the best fit, we had to use a fixed Manning's N value of 0.3, which seemed pretty high for us. The textbook value is 0.06. So we hypothesized, is that warranted, or is there something else, some other flow mechanism at work that we've not really accounted for? And this is where we consider what actually is represented with direct rainfall. So we've got rainfall in the form of precipitation, or precipitation in the form of rainfall being applied to our surface. We have infiltration. Within the subsurface, we track a soil water level. Once that soil water level reaches our 2D elevation, then no further infiltration can occur. It's considered saturated. Everything that doesn't get infiltrated becomes surface runoff, and then that flows off. We can have some evapotranspiration if we wanted to, represented as a negative rainfall boundary, essentially, and then that surface runoff enters our streams. That's what we're representing when we do direct rainfall modeling. That is what all the other software packages out there that do 2D direct rainfall modeling will represent. However, there's a whole host of subsurface processes that we aren't representing. So we get infiltration. That infiltrated flow doesn't just sit there in the soil water. It actually moves in a horizontal sense through what we call interflow. It can move further in a vertical sense through drainage and recharge into the groundwater zone, and we can have groundwater flow as well. So it's these kind of components that are typically ignored by direct rainfall modeling. And we went away and we actually put in functionality, and we'll discuss this later, but it allows us to represent the various different soil layers, and it allows us to have this interflow. So we have a vertical movement of flow, and we have a horizontal movement of flow as well. And where that interflow comes out, once our soil layers become saturated, we get what's known as return flow, and that can feed back into our streams and rivers and drainage systems. We switch that on and we run this simulation again. We actually then can get a very good correspondence with the observed data, but this time using a Manning's N value of 0.06. So that 0.3 was probably representing that slow response to rainfall through interflow. So we switch interflow on and we can use, standard values for the Manning's N values. So the benefit of interflow and also depth varying roughness, which I've not really covered there, but that also has an impact. And that, that interflow really gives us the answer to not all river flow is from direct runoff. We are representing that base flow. We are representing that slower response of rainfall. And then another thing we've added, which I'll touch on briefly, is the drying of soils during periods of no rainfall as well. So we can actually use evapotranspiration to take water away from the surface, but we can also take it away from the soil layers as well. Any question there, Arno?
Yes, 2 questions before you switch to interflow. If I'm correct, TUFLOW allows also the subgrid sampling for the soil parameters and Manning's, right?
It does, but we wouldn't recommend it at the moment. There's
okay.
Yeah, I wouldn't. Yeah, we have that functionality and we have investigated it. Certainly with the Manning's, it provided a few unusual results that we were still trying to investigate and do some more benchmarking. So for the moment, we wouldn't recommend using it.
Okay, because we've seen quite an influence of this parameter on HEC RAS models. So it's linked with the consideration of SGS with DTM. It's still something that we are trying to investigate, but we have seen that activating this kind of options could have a very big impact on the results. And we don't know yet which is the best result in our HEC RAS model. So, yeah.
Okay, so, possibly one to cover in another webinar, but certainly with subgrid sampling, the one thing you do need to be aware of is to make sure that any hydraulic controls are suitably enforced. So the use of brake lines, for instance, you probably need to be a bit more proactive with than using a single elevation point per cell.
Yeah.
So we end up with these things called leaky embankments, which there's various tools that exist within TUFLOW to identify those, but also be proactive and set them up in advance. And possibly that's something we can set up for another webinar, going through those kind of things.
Right. And second question before leaving Quentin asking his own on rain on mesh methods. Do you need to prepare some kind of hydrologic ready DTM, like filling the lowlands and so on? Because we've seen that also this can have some big impact on the first losses, with the first part of the rainfall just filling all the ponds and so on.
Yeah. It depends. I'll be honest with you, in the UK, all the LiDAR data and the DTMs that we would get would be hydrologically corrected in advance of us receiving them. So I'll be honest with you, I don't really know. I suspect you probably would want to hydrologically correct them. What we found is, and this was what I was alluding to earlier when I talked about the wider benefits of SGS to direct rainfall, is that if you don't have SGS, what we found is that, those low points in the upper catchment, for whatever reason, were leading to water being trapped in the upper catchments. And, some of those locations were quite deep as well, which led to a very small time step in TUFLOW HPC. So actually we found with turning on subgrid sampling, although you have those sinks, and then like you said, they're leading to essentially depression storage at a catchment scale. By switching on subgrid sampling, we stopped water being trapped in those locations. It could actually find a route out, and we avoided that deeper flow. And actually, that led to a reduction, quite a significant reduction in the runtime, because we didn't have those deeper flow, and we didn't have the very small time steps associated with that.
Yeah, thanks. Maybe one question from Quentin before.
Yes, can you hear me because I'm outside? Okay.
Yep.
Yep. I was wondering if the hydrological infiltration parameter are averaged on the cells on the cell, or is it only the centroid soil layer which is the reference?
It's if I understand your question correctly, it's on the soil layers. So we can have a number of different soil layers, which can be
on the same cell. Yeah. For instance, two different soil category crossing one cell.
No. At the moment, it's only possible to have a single soil type. That's what that's similar to what Arno was alluding to there with the subgrid sampling of the soil parameters. At the moment, that's not possible, but it is something that we have on our list of things to put into the software.
Yeah, especially because when we are working on a big drainage basin, it's okay. It's not too important. But when we are doing a direct rainfall in an urban areas with a smaller cell size, sometimes it could have an impact to take only one infiltration parameter at the centroid of the cell, or to be able to average different kind of filtration parameter, etc.
Yeah, absolutely. That is, like I said, it's something that's on our development list already, something for the future. There's always the possibility to, manually do that if required. You can look at the interface and maybe have a different soil domain for that interface, so you can average them out. But there's probably a bit over the top in most instances to do that manually. So hope, with a bit of luck, we'll be able to get that subgrid sampling of the infiltration parameters in pretty quickly.
Okay. Thanks.
Great. So if we just continue, so this is just showing you a longer term simulation. So I think this is about 3 weeks worth of simulation. This is what we got with without using interflow. So this was just the standard direct rainfall approaches. Not too bad a job at picking up some of the peaks, but we're really not picking up the base flows. Switch on interflow, we're doing a bit of a better job, and at the time this was rushed through to get it ready for a conference, but I reckon we could probably calibrate this a bit better and get an even better fit with the data. Just another case study. So I showed this one and people were like, well, it's a very small catchment, 13 square kilometers. This is a much larger one, 274 square kilometers in Cornwall in the southwest of England. These are the parameters that we have for our 1D rainfall runoff models. So what this is saying is, it's pretty wet. There's a high proportion of runoff. There's a fair amount of base flow influence. And there's not that much artificial influences to the hydrology. So there's not a lot of reservoirs or lakes or weirs or things like that. This was a 5-day simulation. The black dots are the flow, observed flow. This is the best match I could get with using conventional direct rainfall. So, we're picking up this first peak. We're picking up pretty well the first peak of the second event, but we're really not getting the volume here. We switch on interflow, and I was actually pretty gobsmacked by the outputs. Picking up that first peak again, probably over predicting that peak there, but what we're doing is really picking up the volume associated with this second event. So really quite impressive just by switching on the interflow in this instance. Looking at how we do these kind of things in practice. With 2D rainfall runoff, we are using the 2D hydrodynamics. There's two ways we can do this really. The first is we can actually use a source area, which allows us to apply runoff to the 2D surface. So it allows us to apply the flow directly to the 2D surface. We could pre-calculate what the runoff is and then apply that. However, more and more people are moving towards the direct rainfall, which allows that spatial distribution of rainfall, but also the spatial distribution of the runoff volume generation. In terms of spatial rainfall, there's a couple of 4 approaches to doing this. We can use a global rainfall boundary, in which case we just say, right, our whole model is receiving this amount of rainfall. So we just have a single rainfall boundary, and we can apply that within the TUFLOW boundary control file. We can have spatial variation based on polygons. So we read in different GIS RF polygons, and each of those can have these temporal and spatial adjustment factors. So we can use these as essentially we can use these as fixed runoff parameters if we wanted to as well. Or we could use gridded rainfall, and there's a couple of different ways we can do that. Or we can use the rainfall control file, and what that allows us to do is to specify locations of rain gauges, and then TUFLOW will do some kind of interpolation between those. In terms of reading in gridded rainfall, TUFLOW can use ASCII files, it can use float files, and it can now use geotiffs. So these would be ASCII floats, geotiffs with the rainfall depths, the spatial rainfall depths set up. Obviously, those kind of grid formats are what we call flat formats. They have no time varying component to them. But what we do is we read in a CSV file, which basically says, at time 10 hours, we read in this grid. At time 10.1, we read in this grid, etc., etc. So we provide the time varying component within a CSV format, and we just read in a different ASCII or float or geotiff to give us that rainfall. Our time steps don't need to be constant, and there's no interpolation between the various time steps in this instance. Alternatively, we have a NetCDF format, and NetCDFs do allow both the spatial representation and also the temporal dimension as well. Arnaud?
Yes. In the time column, can we use dates instead of relative time steps?
No, like everything with TUFLOW, it does need time in hours, unfortunately.
Okay. Thanks.
Yeah. Gridded rainfall is less memory intensive, so that's why it's quite commonly used. And the command is always within the TCF rather than the TUFLOW boundary control file, the TBC, and that allows rainfall to be applied across multiple domains. Less important for TUFLOW HPC models, but was pretty important for TUFLOW classic models. Alternatively, we can use a rainfall control file, and this allows us to specify the locations of our rain gauges, and then we can use a number of interpolation approaches. So we can have a TIN approach, an inverse distance weighted approach, or a polygon approach. What we do here is we just specify within our TCF a TUFLOW rainfall control file, a .trfc. And within that .trfc, we have a range of different parameters. So we specify what format we want to create the rainfall grids in, ASCII, float, NetCDF, or geotiffs now. We specify a rainfall grid cell size. This is optional. If we don't specify that, then the cell size or the rainfall grid cell size that's used is 10 times the hydraulic cell size. And then we can specify different grid size for our rainfall grid and a different origin to that grid as well. Then we read in our rainfall points. So these are just a vector data set of where our rain gauges are. And then there's, depending on the method you use, there's optional commands to control both the inverse distance weighting or the interpolation that takes place. So in this instance, what we have is we have our model domain. That's this black polygon. We have a series of rain gauges within our model domain, but also outside of it. And then each of these has a observed profile assigned to them. And what we can see in the grid is the interpolated rainfall based on an inverse distance weighted method. We can see, we've got some, let's just say probably low rainfall here, but some quite high rainfall here. So we're representing that that interpolation between those rain gauges. We can do a tin approach, and in this case, not only do we specify the rain gauge locations, but we can specify the triangles that we interpolate across. The rainfall depths are specified at the points and then interpolated. And it's just important to realize when you're using this tin approach, there's no rainfall outside of these polygons. So if we contrast that with the inverse distance weighted approach, we've got rainfall outside of our polygons. And if, in a different study, we're using or we're modeling this part of the or this area, then we could reuse the grid for that. In this instance, there's no interpolation outside our triangles, so we wouldn't be able to reuse that. Alternatively, we could use polygons. So this basically says, all the cells within this polygon will take its rainfall profile from this location. And that's very similar to the 2D RF approach. But it is more memory efficient. So, if you've got very large areas, this might be something to bear in mind, using a grid, using the interpolation approach, rather than using 2D RF polygons. This is an example. So this is actually using design rainfall profiles. So there was a design rainfall grid on a 5,000 foot basis. And this is the US, so obviously English units rather than SI units. So each of these had a design rainfall profile associated with them. We used a tin, the triangles were defined, and then we have the resulting rainfall grid, and that captures that spatial distribution of the rainfall and those rainfall gradients that might exist within our catchment. The really neat thing is, I don't think I've got a slide for this, but once you've generated, so whether you're using inverse distance weighted or tins or this approach, once you've used the rainfall control file, you generate the grids. So they will be generated in whatever format you specify. On the next occasion, rather than regenerating it, what you can actually just do, this file gets created automatically. You have all your rainfall grid files generated by TUFLOW. For your subsequent simulations, you can just use this approach. So the first time you use that rainfall control file to generate those grids, and then the second, third, fourth, fifth, sixth, etc., just use the rainfall grids directly, and that's a bit quicker. And particularly if you're doing things such as scenarios, it just stops your model files just being completely overrun with all these different rainfall grids, because it will give them a slightly different name depending on the actual simulation name. So set it up once using the rainfall control file, and then use the grids in subsequent simulations. In terms of losses, there's two types of losses, and we touched on this previously. There's the initial losses, which represent to a certain degree some of the interception, and also the wetting losses at the beginning of the events. So there's a small level of depression storage. Also, there's some losses associated with, particularly in urban surfaces. If you've got quite often you have quite a hot urban surface, and as rainfall falls onto it, the first bits of rainfall are actually evaporated because they cooled the surface. So we have those initial losses, and then we have those continuing losses, which represent both evaporation and infiltration. In terms of evaporation, and another common approach is actually to use a negative rainfall boundary, and that allows us to take water away from the surface, and that can be spatially distributed in the same kind of way that positive rainfall can. Two approaches to losses. The first is what we call rainfall excess. So this we specify within our materials layer. We can specify two parameters, our infiltration loss and our continuing loss. And these are applied to the rainfall before it hits the surface. So this water doesn't actually hit the surface. It's just taking out the rainfall before it does. So we add those in with the materials file, or we can specify global values if we wanted to, using the global rainfall initial loss and the continuing loss. The other approach is to use infiltration models. This is probably more realistic from a physical sense. This applies the rainfall to the surface, and then it infiltrates that water from the surface. So if you've got, top of a hill, or you can have rainfall fall on top of that, but obviously it's going to flow away. So you're not going to get too much infiltration from there. Whereas, at the bottom of a valley, you might start to get some infiltration, and it will probably be quickly saturated. So the infiltration approach applies the rainfall to the 2D surface and then removes the water, infiltrates that. Three general types of infiltration. There's initial loss, continuing loss. That's slightly different to this one because this is, like I said, this is taking the water away from the rainfall before it hits the surface. This is infiltration and continuing loss from the surface itself. We have the Green-Ampt model and we have the Horton model. We can also, within the materials layer, we can specify a fraction impervious value for the overlying material. So this is kind of used where we might represent the same soil type that could be under a road, or it could be under a forest, or something else. So we can specify a value between 0 and 1. 0, which is the default value, is 0% impervious. So what that means is that all the soil essentially infiltrates. 1 is 100% impervious, i.e. we don't have any infiltration, or we could specify a fraction between 0 and 1. So in this instance, our roads have got an impervious fraction of 0.9. So that means only 10% of that area on a cell-by-cell basis is available for infiltration. So it will factor the infiltration into the soils based on that impervious fraction. In terms of the infiltration, we spatially distribute it using a 2D soil file or 2D soils grid, or 2D grid. And then we specify the various parameters within the TSOLF file. So we basically specify whether we're using the initial loss continuing loss model. And then in that case, we specify various parameters, Green-Ampt model, Horton, or we can specify that to none. We read in the soils file within the TCF, and then we spatially distribute the soils in the TGC. So just like we would anything else, materials layer, for instance, we can set a global value. We can read in vector data sets, or we can read in grid raster data sets to define our variation in soil materials. And then in our TSOLF, we basically just use that, and we use the various columns to define our models that we're using and the various parameters that we're using for those models. And there's slightly different ways of being able to do this, particularly for the Green-Ampt. We can specify it on a USDA soil type approach, or we can actually specify the various parameters explicitly if we wanted to. We can also have a simplistic groundwater. So what we do by default is if we have infiltration into the soil, essentially we could have that soil is infinitely deep, and we can have pretty much an infinite amount of infiltration. What we can do is have a groundwater depth, and what that means is when we get infiltrated water into that, our groundwater rises. And once that groundwater gets to the point of the 2D surface layer, then no infiltration occurs. It's considered to be saturated, and then no more infiltration. Using this approach, there's only vertical filling of what we call the groundwater or the soil layer. There's no horizontal movement. And just like anything else, we can set that globally, read in a vector data set or read in a raster data set, and then we can also look at the outputs in terms of the depth to groundwater or the groundwater level result parameters. I mentioned depth varying roughness. So for most applications that we look at, Manning's N is independent of depth. So that's what's been shown in this area of this plot here. When we look at ocean modeling, Manning's N isn't necessarily independent of depth. And when we're looking at very, very small flow depths, Manning's N isn't dependent on depth either. And that's when we consider millimeters of depth and you think of your common bed resistance, the scale of that bed resistance relative to the depth of flow is, they're quite similar compared to when you've got deeper flow. The influence of the roughness height is much less. So we do allow you to have these depth varying roughness. And to do this, what we do is we specify pairs of values. So for our material, rather than just having a single Manning's N value, we say, okay, this is the depth. So at a depth of 0.03, our Manning's N value is 0.1. At a depth of 0.1, our Manning's N value is 0.06. And then it's interpolated between. So in this instance, up to a depth of 0.03, our Manning's N value is 0.1. Above a depth of 0.1, our Manning's N value is 0.06, and then it's linearly interpolated between the two. So we can do this, quite commonly done for grasses. If you think of as your water depth increases, your grasses start to bend, and there's a whole host of tests you can do with this. I've done it in the past. You chuck a board onto it and see how much your grass bends. Even some what we probably consider quite rigid vegetation does have some kind of bending associated with it. And also another approach is to use it for buildings as well. So you allow a small amount of flow at low depths, but at higher depths, you essentially try and retard flow going into that building footprint. You can, if you want to, if you use the map output type N, you can then map what the time varying Manning's N is. So we can see that during the simulation. So you can see here, we've got darker areas here, which I presume is a higher Manning's N for whatever reason. Oh, sorry, probably a lower Manning's N actually, because we can see for the buildings, our Manning's N has increased quite a bit as it's gone into that yellow color. So we've got the change in roughness as a consequence of the flow depths. Just a couple of things to consider when doing direct rainfall modeling. If you are using TUFLOW Classic, which I assume most people aren't, but if you are, that solves water quality, solves water surface elevation as one of its state variables. And as a result, if your elevations are quite high and you're using direct rainfall, so you're looking at millimeters and possibly sub-millimeters of rainfall, you can have floating point imprecision. Therefore, if you're doing direct rainfall modeling with TUFLOW Classic, we would recommend you use the double precision version. That's not an issue with TUFLOW HPC because it's actually solving depth rather than the water surface elevation. So you can use the single precision version, which is great because that's quicker, particularly when running on GPU. Another thing to bear in mind is that the default sal wet dry depth in TUFLOW is 0.002 meters. However, if you are dealing with direct rainfall, again, you're dealing with millimeters and sub-millimeters of rainfall depth, then you probably want to just reduce that to 0.0002. Hopefully I got the right number of zeros then. Arno, you got a question?
Yes, we have a question from Maxime. Is there some runoff modeling uncertainties regarding high slope terrains?
Not that I'm aware of. This often comes into play. It used to be an issue with TUFLOW Classic. I've not come across it with TUFLOW HPC, and we've done some quite high slopes. So yeah, I don't. I'll be honest with you. I don't know what the issues are with Hecres and other solvers, but I've not seen them. But if you do come across them, please let us know.
Okay, and on this question, what could be the kind of slope limit for TUFLOW HPC?
I don't know. I'd have to get back to you on that one.
Okay, I guess at some point we have some air entrainment and so on with bubbles, which could be the limit, but okay. And last question regarding the default cell wet and dry. This is the limit used for the model, which is different from the mapping cutoff.
Yeah, exactly.
Okay. And is there some when we modify this limit, is there some way in the log file to track the volumes, to check if maybe this limit was too high and we've lost too much water?
What you'd probably do if this value was too high is your mass balance errors would be a bit higher.
Okay.
Excuse me. So yeah, always keep an eye on your mass balance errors. And particularly if you're doing direct rainfall modeling and your mass balance errors come quite high. This is usually the first culprit that should be looked at.
Okay, thanks.
You can, more result parameters when you're doing direct rainfall. So you can see the cumulative rainfall and the instantaneous rainfall rate. You can look at the cumulative infiltration and the instantaneous infiltration rate as well. So yeah, in terms of outputs, you've got that full visibility of what's going on.
I would add on this question, if you do some direct rainfall modeling, these kind of variables are very interesting to look at to understand what's happening in your model. We've done a few tests, and this is quite interesting to track the infiltration versus time and so on, especially with in link with your spatial rainfall, I think. When you want to really understand what's happening in your model, it's good to have a look at this kind of results along depths and velocities on the flooded side of the model.
Thank you. In terms of runoff generation, there's two main processes. So there's infiltration excess or rainfall excess, or sometimes called Haltonian flow. And this happens when your rainfall rate is greater than the infiltration capacity of the soil. So you might have a rainfall rate of 10. Your infiltration capacity might be, a rainfall rate of 10 millimeters per hour. Your infiltration rate might be 8 millimeters per hour. Obviously, that 2 millimeters of an hour can't get into the soil, so is infiltration excess and then forms runoff. Outside of temperate regions, in temperate regions, that's actually quite rare, particularly outside of urban areas. What tends to happen in temperate regions is that our rainfall rates are pretty low. Although it rains all the time in England, the rainfall rates are quite low. Our soils can infiltrate quite a bit of of water. But what happens is though the constant rain saturates those soils, and we get what's called saturation excess runoff. So what we mean by that is our soils get more and more saturated to the point that they can take no more water, and then we have runoff generated that way. So infiltration excess is represented by those infiltration models, the Horta model, the green ant model, they all represent that kind of process. They also, certainly with the Horton and the green ant, is that the infiltration rate reduces as the soils become wetter. But we can also then use that defined groundwater level to say, you know, once our groundwater level gets up to the cell elevation, then we don't get any more infiltration. And that's what's been shown on this graph here. So you know, we can plot up the rainfall rate, we can plot up the infiltration rate. We've got the rainfall rate in blue here, we've got the infiltration rate in pink, and then we've got the flow depth on this particular cell. And in this instance, the flow depth is essentially a proxy for runoff generation. So in this instance here, our rainfall rate is greater than our infiltration rate. We have the flow depth increasing, so that's runoff being generated, and that's what we call infiltration excess. We have this period here where our rainfall rate equals our infiltration rate, so no runoff is being generated. And then we have a situation here where our soils have completely saturated, and then you know our infiltration rate drops to 0, but we still have runoff generated, so that's a saturation excess. So we've got the two main processes of runoff generation being represented. But the big question is then, you know, what happens with the infiltrated flow? So traditionally, this is just lost to the this would just be lost to the model domain. But that's where interflow comes in, because we can now start to track that both within, you know, it could further infiltrate into the soils, or it can now move horizontally. So, you know, that infiltrated flow can be lost via evapotranspiration. It can percolate further down into the bedrock, or it can travel laterally through the soil or through the rock as groundwater flow or interflow. And in temperate environments, that's where a lot of our water reaches a river through those through-flow, interflow, through the soil layers, through groundwater flow, and it provides that slower response to rainfall. Rami?
Yes, before we dig too far into interflow, a question from Gail. If we want to apply a very simple approach with a fixed constant runoff in coefficient, the best way could be through the impervious fraction?
No. So if you're doing percentage-wise, so that's the impervious fraction will impact the amount of infiltration that can occur through one of the soil infiltration models.
Mm-hmm.
So it's not just a fixed percentage, it would be a fixed percentage of the continuing loss, for instance, or a fixed percentage of the green amped or the Horton infiltration. The way to use a fixed percentage would be to use the 2D RF polygons.
Mm.
And to apply that as a factor within there. Let me just see if I can, probably not worth going back to it just now, but I can shoot across the screenshot. I think you've done that in the past, haven't you, Arno?
Yes, I've tried. It's one of the way we do that actually. Yeah, it's if we want to do very simple models with just a specific percentage for each soil or land cover. Yes, now we use 2D RF polygons. And if we use this fraction in conjunction with infiltration model with infinite infiltration with dummy values, can we get the same?
Yeah, I guess so. I guess if you use the initial loss, continuing loss model, maybe set initial loss to 0 and maybe have a very high continuing loss. Yeah, I'd have to play around with that. But yeah, you might be able to do it like that.
Okay. I think I will add on this subject. Always do some sensitivity test on the values, that just to check that the model is reacting as we expect. And because sometimes we can have some strange results, and not only with TUFLOW, but with all this kind of models with direct rainfall. So we need to check that the configuration we have done gives the results that we kind of expect.
Yeah, I'd always recommend if you're doing any kind of calibration or something, play around with the values, change them, by 50% higher, 50% lower, and just see, what happens with each parameter.
Right.
And there's some interaction between them in a certain way as well. But always worth getting an understanding very quickly. And yeah, that's where something like subgrid sampling can come into its own again as well, in terms of understanding those relationships.
Okay.
So obviously, yeah, interflow gives you that slower response to rainfall. It can also lead to further saturation, or further saturation excess. So particularly at the bottom of valleys, I was quite shocked walking around some of the hillier areas of the UK last year during drought, and there was water just flowing out to the bottom of the slopes, still coming out. In fact, actually, we had some. I live about 100 yards away from an old water supply pump. I live quite high up a hill, a moderately sized hill, and it's rained that much in the UK this winter already that water is just spilling out of that pump. And it's just, that interflow from elsewhere is just coming out at that location. So that, causes further saturation of the soils where you might not expect it. Well, maybe you will expect it, and then gives you that return flow back onto the surface. So the interflow is based on a 2D implementation of Darcy's law for flow through porous media. And what we're doing is essentially calculating the water table in each cell layer. And then the vertical movement of flow is based on the vertical hydraulic conductivity and obviously the cell area. We then have the horizontal movement of flow, and that's based on a horizontal conductivity value, a porosity value, but it's based on the essentially what we call the groundwater pressure level. And that groundwater pressure level is usually the difference in the water level between two cells. In a unsaturated case, in a saturated case, it would be based on the pressure level, maybe in the water level above it. And where our top layer is completely saturated, then that would be return flow back onto the surface. That's the kind of thing that's going on. Quick example, small example. So this is essentially two buckets with an embankment in the middle. One at a higher elevation, one at a lower elevation. And the embankment's a meter higher. We've applied 800 millimeters of rainfall on the higher of the two areas, and we've run it with and without interflow. We've got one soil layer going on. So this is what happens when you haven't got interflow. So we've got runoff occurring, our water depths increase, but it never gets to the point where it can flow over that embankment. So we don't get any water in the downstream bucket. If we switch on interflow, we've got infiltration, we can track that within the soil layer. We've got infiltration excess, and then our water level gets up to the surface, so we start to get saturation excess. But again, our water level never gets high enough to spill over the embankment. But what you might be able to just see is the water moving through the soils, and then it starts to come out in this lower bucket. So a very simplistic case, but that's what's going on with the interflow functionality. We use the soils in the same kind of way. So the soil is essentially, that's what controls our infiltration. That is what we call soil layer 1. So if we use the set soil command, we are setting this the infiltration parameters for soil layer 1. We can then specify the soil layer parameters, and TUFLOW can have up to 9 soil layers. Now, some of the data sets that are out there, the European Soils Data Center, for instance, I think they have 6 or 7, I can't remember precisely, but they have data for 7 different layers. I would really recommend keeping it simple. I would probably never use more than 3, and possibly 2 in most instances. I've yet to see the real benefit of using 9. I dare say there are, but yeah, for the time being, I'm just using 2 or 3 myself. So what we do, we basically say set soil layer 2, and then we set a soil layer for that. And again, just like we can with the infiltration models, and we can spatially distribute that. We can spatially distribute it based on vector data, or we can do it using raster grid data. If we've got multiple layers, then we can set the thickness or the base elevation. So, we can either specify it 2 meters above datum, or we can say a thickness. So whatever the ground model level is, our 2D cell level is, minus whatever our thickness is, and we can start building up our the composition of our soil layers using this. And again, that's going to be or can be spatially distributed, so we can read that in using vector data, or we can use that use grid data to define that. We can, if we want to as well, set initial groundwater layers, and we can do that in individual layers as well. We don't necessarily have to have the same water level in each one. And we could say, actually there's a small amount of water in layer 2, but there's nothing in layer 3, and there's some in layer 4, for instance. And again, we can spatially distribute that if required. And then once we've done that, we start to add in the various interflow parameters. So for soil layer 1, the topmost soil layer, that's what controls our infiltration. So we use our infiltration models in the same kind of way. We specify an initial loss continuing loss model, or a green amp model, or a Horta model, and we specify the parameters which control the infiltration into the soils in the same kind of way. What we do have is an additional horizontal conductivity parameter. So this governs the horizontal movement of flow in the subsurface. That's in units of millimeters per hour. I would be aware of that, because I've done a fair amount of reading on soil parameters and characteristics. I've never seen one parameter have so many different units in any other aspect of hydraulic modeling. It seems to always have slightly different units. I've seen millimeters per day, I've seen meters per hour, meters per day, millimeters per hour. Keep an eye out on what the units are and make sure you're applying those sensibly within TUFLOW, which requires millimeters per hour. In the past, when specifying soil layers, you didn't necessarily have to specify a porosity, but that does need to be specified within the soil layers when using hydraulic conductivity. For soil layers 2 to 9, so i.e. not the top one, not the one that's controlling the infiltration, but the lower soil layers, where you might have or want to represent interflow or groundwater flow or what have you. We have this new convective hydraulic conductivity. It's set up as an infiltration method, but obviously it's not an infiltration method, it's an interflow method. And to that, we specify the hydraulic conductivity. So this controls the vertical movement of flow. We can specify a porosity to our soil layer. We specify an initial moisture if we want to. And then we can also specify this horizontal conductivity. So we've got hydraulic conductivity, which specifies the vertical movement of flow. And then we've got the horizontal, which obviously doing the horizontal as well. Boundary conditions. So at the edge of our 2D domains, we can have either a sealed boundary, just like a bucket, or we can specify a water table as an elevation boundary. So we set the edge of our domains to a GT type boundary. But in the future, we will be adding more boundary conditions at the edge of our domains. We can use the grid check files. So once we set these up, whether it be setting them up using set commands, or whether we use vector data sets or gridded data sets, we can check what the various levels of our individual soil layers are. So on a cell by cell basis, we can look at the groundwater soil layer levels. In this case, I've got 4 soil layers, and we can look at the initial groundwater within those layers as well. Results are updated as well, so we've got the general ones that we had previously, but this time we've got the groundwater depth within each layer, the groundwater level within each layer, the groundwater moisture within each layer, groundwater flow within each layer. So we can do some quite nice mapping actually of groundwater moisture and within our soil layers, and identify those layers that are saturated. We can also use vectors. So in this instance, what we're seeing is the red lines is the surface river network. The black lines are the subsurface movement of flow. Forms quite a wider drainage network, really. And then we can do, as we have done, as I've shown you, we can start to use the QGIS tools and actually plot these up both as time varying data and also as long profiles or cross sections. We can use plot outputs as well. So if we want to get information about specific locations, maybe it be groundwater boring hole data, we can compare that using PO points. Or if you're wanting to get flow through a line or volume within a particular region, then we can get those kind of things out as well. We can also use negative rainfall to dry out soils. So this has been possible in the past in terms of applying negative rainfall to evaporate storage water, surface water. So we basically specify a negative rainfall value. However, what we can do is where there's no surface water, we can say actually take that rainfall out of the soil layers. So it will take it from the top layer. And then we can just factor that by a specific amount. So it could be that we take 100% of that, or we take 50% of it, etc., etc. So just quickly, Arno, I just go for these next couple. This slide here. So this is just showing the influence of that drying of the soils. So it doesn't obviously where we have rainfall doesn't have a great impact, but further down the line, we start to differ from what we would have if we didn't have that drying of soils. So, Arno?
Yeah, just on the slides before, we were speaking about water table measurements. Were you able to kind of calibrate on some models what TUFLOW was giving versus this kind of data?
So the way that I've been using it, I think there's a distinction really a little bit in terms of the way that I'm applying it, which is not necessarily groundwater modeling. I think we need to be careful as to what we're trying to model here. So I would use it as that kind of interflow and that soil movement of water. So for me, we're looking at the longer term response to rainfall, but I'm talking days or weeks. I'm not looking at the groundwater flows coming through weeks and months afterwards. So I've not done any groundwater modeling myself. I would probably suggest that it's not, there's better tools out there for proper groundwater modeling. I dare say it would give you some good answers, but I'd be a bit nervous about applying it in a proper groundwater dominated catchment. But that's not to say it couldn't be done. I know some of the guys in Australia have done some very good calibrations, but I've not seen anything myself where it's been compared to groundwater borehole levels, for instance. But there's no reason it couldn't be. And likewise, soil water level measurements as well. We've got a few of those in the UK. Pretty sparse, but it could be done. Okay, thanks. I think I'm coming towards the end. So this is an example of just using those soil layers in a slightly different way. They could be used for assessing assessing low-lying areas, for instance. We've seen quite a bit of quite good use of them there. SUDs, I don't know, or lids, sustainable drainage systems. They're often made of different substrate layers with different hydraulic properties. We've used them in that sense. But we've also just started adding in tracers to this. So this is exactly the same simulation. And what we have is a pollutant which exists within subsurface layer 1. So it doesn't exist on the surface, just within subsurface layer 1. We've applied direct rainfall to that. It starts to infiltrate. Our concentration starts to reduce, and it starts to move. It gets to this low point into this drainage channel, and then it starts to spill out onto the surface. So now we have this pollutant, which was only in soil layer 1, starting to come out onto the surface, and obviously once it's out on the surface, it moves more freely than it did in the subsurface. So we can now start to put tracers into that interflow. So whether that be, in this instance, we've got a soil store of a particular pollutant, but we could have a pollutant on the surface which gets infiltrated into the soils, and then we could track the movement of that pollutant both on the surface and within the various soil layers as well. So that's quite an exciting application into the water quality world that we're going into in terms of using that direct rainfall approaches, using the interflow, but actually using it from a water quality point of view rather than a water quantity point of view. And there'll be some quite exciting announcements of where we're going with that with TUFLOW. We're developing a new software product which kind of utilizes that kind of approach. So that is my last slide. So I appreciate, as always, whiz through direct rainfall modeling, but hopefully gives you a bit of a flavor as to general things that you can do with TUFLOW. I think it would be probably worthwhile having a session on subgrid sampling at some point.
Right.
And we have a I think we have an opportunity later in the year. Greg Collicutt, who's the guy who wrote TUFLOW HPC, is over in the UK, so we might have a session later in the year. He would be able to very much answer the question about the TUFLOW HPC what's the word I'm looking for? The appropriateness of TUFLOW HPC for higher gradients. He'd certainly be able to answer that.
Okay.
So yeah, happy to answer any questions as always.
We have one question. I don't know if you can see them, Duncan, on the conversation.
Okay. Yeah, so groundwater. Yeah, so we can apply a time varying groundwater level. So in TUFLOW speak, we have a HT boundary which applies a water level boundary, a time varying water level boundary to the surface. We have a new GT one which applies a time varying groundwater level. So we can use that to add flow into the subsurface layers.
Thanks. Question from Quentin regarding the SCS.
Yeah, that's on the development pipeline. I don't know where we are with that actually. I'll probably have to check that, but yeah, the intention is to have the 2D SCS infiltration method within TUFLOW.
That would be a very nice Christmas gift, but maybe it's too soon.
I don't for a second imagine it'll be available before Christmas, but yeah, that's certainly something on the agenda. The other thing is the with the interflow at the moment, there's no connectivity with the 1D domain at the moment, but that's something we'll be looking to do. So having infiltration into the soils, having that interflow, and then having it or being able to link that to the pipe network, for instance, might be a very good application.
Oh, that would be nice. I was thinking maybe just Are there still any questions regarding today's webinar? It doesn't seem. Maybe I had two, not question, but can we speak maybe 2 minutes about the swim integration, the timeline for the availability on the on TUFLOW, and maybe a quick word about what you developed on the plugin side for rainfall generation. We've run a few tests, but it's not publicly available yet. So can we maybe just quick word about that?
Yeah. So to go to the swim. So behind the scenes, we've been linking the US EPA swim engine with TUFLOW. This will be available as a beta in the 2023-03 AD version, which should be out in the next couple of weeks. And essentially, you'll be able to. You'll have to forgive me. I don't know the full details, but the swim engine will be essentially integrated into TUFLOW. And you'll be able to take your existing swim IMP files, and I think you can use the IMP files directly, or you can convert it to a geo package. There's various tools that will be available. Let me just see if I can dig it up within QGIS. As always, QGIS takes longer to load up when you want it to load up quicker. But yeah, there'll be a whole host of tools which allow you to put your swim models into a format readily used for TUFLOW, and also vice versa. You can convert them from a TUFLOW format back to swim if you need to as well. And essentially, you'll be able to run swim within TUFLOW, and probably more importantly, connect swim to the TUFLOW 2D engine. So you can, for instance, in urban areas, apply rainfall directly to the 2D domain, link it to a swim representation of the subsurface, and have that bi-directional coupling between the two, and really gives you, functionality that's already within TUFLOW. But I know many people are very familiar with swim, and it's got a lot of traction in many parts of the world.
Right.
And just bear with me a second. So what you'll see within QGIS, if you have the TUFLOW plugin installed, there's now a whole host of model files, processing scripts within here, and you'll see now there are these swim ones. So there's a whole host of ways now of converting your model, creating a geo package, TUFLOW geo package from the swim IMP file, writing back. There's various integrity tools, various things to do with assigning losses and creating those connections between the 1D and 2D domains. So yeah, I'm hoping, fingers crossed, that version will be will be out next week, which will have the swim linkage as a beta.
Thanks. Sorry, it was not meant as a trap.
No, not at all. And then the other one is this rainfall generator. I'll be honest, I've not used it for a while. I've passed it over to Arnaud to test. But this is a tool that Arnaud's asked us to develop, which is using the French Montana rainfall generator, where we can specify the storm duration, the position of the peak, various Montana coefficients, single triangle or double triangle hydrograph or hyetograph, and then it will go away and put that into a TUFLOW format. This is something which we've developed, passed to Arnaud for testing. I think Arnaud's happy with it. We'll stick that within the processing tools at some point, but probably in the first instance, what I'll do is I just need to tidy up a few bits and pieces behind the scenes, which I might be able to do this afternoon, I can certainly stick that somewhere so that people can download and use it and test it out prior to us getting it into the processing tools within the plugin officially.
Okay. That'd be a good start, I think, to do a bit of testing.
Yeah, let me.
Okay. And on this, maybe on this subject, I will I will share the links, but there are a lot of resources outside of TUFLOW website and TUFLOW plugin. You have a lot of tools available. I was thinking about the GitLab of TUFLOW with a lot of very specific tools which have been developed by BMT or third parties developers, which are very interesting with scenario management and so on. So I would say for very advanced uses of the software, don't hesitate to ask some question. We can point to different resources which are very interesting. And I will also share a question regarding maybe next subject for webinars. I was thinking about very interesting things I've seen on geo packages and versioning of models. It could be a good subject, maybe for next year, because it's quite a complicated subject, but a lot of possibilities regarding GIS and models management.
Yeah, absolutely. And we can get Ellis to do that. I just very quickly, if you don't mind, now that I've got QGIS open, I might just very quickly show you something that Ellis has developed, which I think might be of interest. As per usual, I'm not going to be able to find it. And let me just get a text editor open. And apologies if I've shown you this before. I don't think I have, but just in case. So if you download the latest version of the TUFLOW QGIS plugin, what you can do now is if you have your TUFLOW layers open, so you go through the approach of maybe you import your empty file or you insert your TUFLOW attributes to the GIS layer. TUFLOW obviously has its template files, but what you can do now is if you right click on those, you can go to TUFLOW, copy TUFLOW command, go to your control file and just hit paste. And it will just read in or generate automatically the correct command, the equals, and then the reference to that file. So whether it's a shape file or map info file or a geopackage, it will read in the correct terminology. And if there's if, for instance, again, not the best data set I've got here, if you've got, hang on, bear with me. It's probably easier if I just show you an animation of this. Hopefully this will work. So if you have, for instance, if we use two layers together, then we can just select those two layers, go to TUFLOW, copy TUFLOW command, and we can paste those into our into our control file, and it brings both those in and knows to use them in conjunction. A very small little tool, but potentially very, very useful. Just means you don't necessarily have to keep going back to the manual to make sure you've got the correct command.
That's nice.
So yeah, certainly on the geopackage and the version control, I think that'd be a very nice one for Ellis to give in the new year.
Okay. I think we are good. Any question? No. As usual, I will prepare a recording, and they should be all available soon, before Christmas, I think. And for any questions, subjects, don't hesitate to contact me. And that's it. Thank you.
Sorry, just very quickly, and likewise, if there's any ideas for some tools on the efficiency side within QGIS or anything like that, please do not hesitate to let us know, and we can see what we can do.
Right. Thank you very much, Duncan.
Thanks all. Speak to you all soon.
Bon appétit et à bientôt. Merci. Bye.
Merci.
Thanks all.
Thanks, Duncan.